all shades of gray, no black and white, has been reabsorbed back into your body. So this is indiscriminate, but these next two functions, reabsorptions and secretions, are very selective. And the net result is most of your pee has the waste. Okay? But like your nephrons are actually reabsorbing urea. 100% of the urea that comes out of the glomerulus does not go in your pee. Your body actually reabsorbs some of it. Okay? It's all shades of gray. All right. This is mostly in the early nephron, and that's why I have more of these arrows going in this direction early. So I'm going to put the 2 right here for selective reabsorption. So most of this is early nephron, but there can be some later as well. And that will be discussed when we talk about hormones that influence or regulate urine production. Active transport is the driving force of selective reabsorption. And out of that 180 liters that are exiting here, 178.5 liters are coming back in, which is why an average adult urinary output is only about 1.5 liters. That's on the bottom of the slide, slide 43. Okay, slide 44 is expanding on this active transport, and it includes both primary and secondary active transport. Both mechanisms are being used, and it's just animation showing that. Since water follows the salt, if you reabsorb salt, water is going to follow as well. Then you got to click through this slide 44, and it removes the one figure, and it talks to you a little bit, and what you want to write on the bottom left of this slide 44 is Lab 8, that we did the glucose tolerance test as a screening tool for diabetes mellitus. This bottom left on slide 44 explains what happens with poorly controlled diabetes mellitus. And this is not just true for glucose, it's everything. Everything that you are reabsorbing has a maximum, and it's because the channels, the protein channels on all the cells, you have a finite number of nephrons. Yeah, you have, 2.4 million. That's a lot, but that's still a finite number. And each of the cells of these tubes have only so many cells, and each of those cells have only so many protein channels or pumps. And because of that, there is an actual maximum of how much you can transport. And that's what it's talking about here. So tie this to Lab 8. If you have too high blood sugar that's flowing in the vascular fork, and it's coming out indiscriminately into the filtrate fork, your nephrons are going to work really hard to get all that glucose back into your body. If there is too much and it maxes out all the transport proteins, that's called this transport maximum, or TM. And you get above that concentration and it spills over into the rest of the urine. Now in the lower part of the nephron, that glucose in the tubes is drawing water. Water follows the salt, water follows the glucose. And that's why it's diabetes mellitus. Because you have too much glucose here in the later nephron, water's being drawn into it, following the sugar, and you pee all the time. Because you pee all the time, you've lost too much water, you're thirsty all the time. So you're constantly drinking because there's too much glucose, you pee it all the time. So you're constantly thirsty, so you're constantly drinking, you pee it all out. That's why it's diabetes mellitus, and it's because the blood glucose exceeds the transport maximum. Exceeds what number 2 can do. And it stays, there's spillover in the filtrate that attracts water. All right, slide 45 is secretion. Again, This, we did actually mention this when we talked about the acid-base metabolism right after the respiratory system. We talked about delayed mechanisms. So the one immediate mechanism is buffer. The two organ systems for the two different delayed mechanisms are the respiratory system and the urinary system. And one of the ways that your urinary system gets rid of excess acid is by secretion. That's what it lists up on the top of slide 45. Now, again, this is mostly later nephron, but you can have some early as well, but more of it is later, so that's why I have more arrows down here. So I'm going to put the third function here. This is the last of the nephron functions. This is still part of the nephron, putting things into the filtrate that your body doesn't want to have there. Okay. Active transport is the driving mechanism as well. And again, after you go through 1, 2, and 3 on a normal adult day, you got 1.5 liters going out in urine. The last function is not a nephron function. So that's getting rid of the urine excretion. So I'll put the 4 down there. So this 1, 2, 3, and 4 are these 4 functions and where they're occurring. Here we have to talk about the micturition reflex. And it's kind of like, why do we need another word? Isn't urination enough for peeing? No, we have to have another one, micturition. Let me know if this link still works. If it doesn't work, I need you guys to do it because I'm just checking too many things online right now. Okay. We have all the slides, all the words there. Let me explain the micturition reflex beyond what's on slide 46. Remember that the detrusor muscle, the smooth muscle coat of the urinary bladder, and it's poorly organized. It's not nearly like the digestive system. Well, you can't control it. And smooth muscle shows dynamic compliance. I think I explained this when I was going over smooth muscle physiology. But if you stretch smooth muscle, it'll contract against it. But if the stretch remains, it'll just shut off the contract against it. So as your bladder fills, it contracts against it and then relaxes. And that way the ureters don't have to fight against pressure because they're doing peristalsis 24/7, but it's not really powerful. And if the detrusor muscle is constantly contracted with too much pressure in the bladder, the ureters wouldn't be able to overcome that pressure. So that's why it fills, contracts, relaxes. Fills, contracts, relaxes. Fills, contracts, relaxes, and then it fills, and the stretch receptors in the wall of the bladder, after a certain threshold of stretch, will send signals up. I think it's the pudendal nerve, but it doesn't matter. Anyway, it starts the micturition reflex, and this is autonomic. You can't control it. And here now, the detrusor muscle will not show dynamic compliance. It'll contract against the bladder, and the only thing that now is going to relax is that internal urethral sphincter. And without you wanting it to happen, urine leaves your bladder. The difference is if you're potty trained, you have trained your urogenital diaphragm to have muscle tone all the time. And part of that muscle tone is contracting the external urethral sphincter, which is part of the urogenital diaphragm. Well, when that urine leaves the bladder, you can't control it leaving the bladder. It's just going to do it. Boom. It hits the external urethral sphincter, and that's when you have this feeling like I gotta go potty. Okay? And it stays contracted until you can get to the toilet, and then you voluntarily relax your urogenital diaphragm, the external urethral sphincter relaxes, And because the detrusor muscle is constantly contracting now, he's going to go out. Okay? That's the McPherson reflex. It's all, you got to hit the stretch threshold. All right, so again, on slide 47, I'm using that same fork in the road thing here and showing you basically where these guys are happening. Okay. And you can look online, the covering figure on slide 47 is just really easy to find, and you got the 4 functions right there. And you got the 4 functions all the way through the collecting ducts. You start to lose the ability to change things toward the end of it, but once it falls off into the minor calyx, your body cannot change it anymore. Okay, now let's talk about some details. We've gone over the anatomy review and the specific but basic functions of the urinary system. On slide 48, this is what's really key for driving, especially function number 2, reabsorption. And that is your kidneys are getting progressively saltier the deeper you go into the kidneys. This is called an osmotic gradient. And the interstitial fluid is getting progressively saltier the deeper you go in. And you can actually see the numbers there. 300 is close to isotonic. And this is why we got to look at the loop of Henle, or the nephron loop, and separate out the descending and ascending limbs.
So let's move this over here now.
We're gonna, and if you have your lecture packets out, I was on the whiteboard, page 70 to 74, and you wanted to start on page 72 because that was a review of the nephron. And now you want to turn to page 73 of your lecture packet, where it talks about the countercurrent multiplier and exchanger. What's really helpful is if we kind of divide it up into 2 separate things, even though they're interdependent, and look at this thing sequentially, okay? So in the countercurrent multiplier, we are looking at the nephron loop. And the key for understanding the countercurrent multiplier is to think this through sequentially. Sequential thinking helps. The difference is that we're not going to look at it in the same order of the flow of filtrate, because you go through the descending limb first, then you make a U-turn and you come up the ascending limb. We're not going to look at it that way, so that way we can just understand it. Okay? Now again, let's start at the base 300, which is isotonic. And you see these numbers on the figure on slide 49 near the top in the cortex and the very superficial renal medulla. That's isotonic, around 300. Okay? Now we got to figure out how is it that our kidneys are making it progressively saltier the deeper down it goes. The interstitial fluid will always be slightly more hypertonic, slightly saltier than the filtrate in the tubes. And that's what we need. So we can, because if water follows the salt and there's more salt in between, then water can, and other things can come out in the filtrate. So it's always saltier here, so you're drawing more things out of the filtrate. And that's the first step of reabsorption, which again is key. So here we're going to look at the descending and ascending nephron loops separately. check out that link as well. That's on slide 50. Let me know if it's any good. Okay, so you want to start, if you're going to do sequential thinking, you want to start with the ascending limb. I know it's not the first one, it should be descending limb first, but to understand it, let's start there. And then we'll go through this sequentially and hopefully it'll make sense. Here, what's really key about the ascending limb is that you have sodium pumps that are pumping sodium, and only sodium, out of the filtrate into the interstitial fluid. What is key here, though, is that these cells in the ascending limb are impermeable to water. Water can't cross it. The only thing that does follow is the chloride, and it's by electrostatic attraction. Since the sodium is positive, the negative chloride follows. So basically, in the ascending limb, we're going to start with reabsorbing salt and putting it in the interstitial fluid. And it's salt and only salt. Because these cells are impermeable to water. This is now making the interstitial fluid more salty. It is also making the filtrate more dilute. So if you look at these two figures on the bottom right of the slide, be sure that you write an arrow on this on the loop. The left side is the descending limb, the right side is the ascending limb. And that's why the red arrows is showing you the salt coming out of the ascending limb. That's where we're starting. So the left side of those pictures is the descending limb, right side is the ascending limb. Draw pictures that you can keep that straight. And it parallels what you see in the picture on the bottom left, with the descending limb being on the left side, ascending limb being on the right side. Okay, we start there. Now, we want to go to the descending limb. And that is permeable to water. And that, since it's saltier now in the interstitial fluid, water can follow the salt there. It can't follow it on the ascending limb because the ascending limb is impermeable to water. Okay, now let's think this through sequentially. If you're on the left side of that figure, and as that fluid is going down, water is being drawn out of it, that's going to make the filtrate saltier in the descending limb as it's approaching the U-turn. That's what it's saying there in the second bullet. So if you look at figure C on the bottom, you can see the numbers have jumped in the descending limb. Thankfully, that is labeled from 300 to 400. That means the filtrate is getting saltier as it's making the turn. Okay. Now the osmolarity is approaching the interstitial fluid, but because of the ascending limb, it is always a little more salty. in the interstitial fluid than the filtrate. It's just getting close. It's approaching it. That's what the third bullet is saying on slide 52. Now, this is why we call it the countercurrent multiplier. Countercurrent because the filtrate is flowing in opposite directions, descending limb, ascending limb. Multiplier because this sequence now sets up a positive feedback loop. And that's what's on this diamond on slide 53. All right, so let's just purple and strong. Okay, here it is. We started here. Salt comes out here. Water's drawn out here. So let's make the salt red. Let's make the water blue. If only water's coming out here, this is getting saltier as it's making the turn. Now there's more salt in the ascending limb to come out, which draws more water out of the descending limb, which makes this saltier filtrate as it's making the turn. Now there's more salt in this filtrate to get pumped out, which draws more water out of the descending limb, which is making the filtrate saltier as it makes the turn. There's more salt over here to be pumped out to draw out more water on this side, which makes the filtrate saltier as it makes the turn. Now there's more salt on this side to be pumped out, which draws more water out on that side, which makes the filtrate saltier as it makes the turn. Now there's more salt on this side to be pumped out, that draws more water on this side, which makes the filtrate saltier as it makes the turn. And then that causes there to be more salt to be pumped out. That draws more water out of this side, which makes the filtrate saltier as it makes a turn. That puts more salt on this side to be pumped out, draws out more water on this side, which makes this filtrate saltier as it makes a turn. Now there's more salt on, you guys get it? That's the positive feedback. It finally maxes out when all the sodium pumps, because it's a finite number, are working as fast as they can. This becomes sodium saturation. That's the end point of the countercurrent multiplier, is when the sodium pumps, which are primary active transport, which means they're burning ATP, and which is why when we went over basal metabolic rate, why your kidneys were listed as one of the organs that is figured in the basal metabolic rate. Your kidneys are going to be doing this all the time, regardless, as long as you're alive, and it's burning up ATP for these sodium pumps. And you can see, we can flip through all the figures on the bottom right, and you can see the numbers just getting higher and higher and higher. And that's when you finally get to these crazy numbers. Slide 54 and 55 is showing you that positive feedback loop and how it eventually gets to 1400. You started at 300, you keep doing this positive feedback loop, and it gets at the turn of the nephron loop around 1400. Some cultures like to eat kidneys in dishes. One of the reasons why some people like to eat kidneys is because it's really salty. I wouldn't eat kidney because I know that's not the only things that are in there. Okay, so that's what slide 56 is telling you, that the end of this positive feedback loop is when all the sodium pumps achieve sodium saturation. Okay, all right, is key, and what I would really write on this, countercurrent multiplier, this is what is establishing the osmotic gradient. And that osmotic gradient is driving function number 2, the absorption. Okay, now let's go to the exchanger. When we're talking about the exchanger, we're not talking about the nephron loop. We are talking about the vasa recta. But here, just like the nephron loop has ascending and descending limb, you have got to understand the vasa recta as having ascending and descending limbs too. It's the peritubular capillary that parallels the nephron loop. So you have the ascending vasa recta and the descending vasa recta. Okay? The key here is this makes it. That's what it basically says. When it says establishes osmotic gradient, it makes the osmotic gradient. The exchanger maintains the osmotic gradient in a very energy efficient way. Because this is burning a lot of ATP with all the sodium pumps. Is this doing this on the whiteboard helpful? Yeah. It's the only reason why I'm shaving and getting dressed and coming into work. I was doing this in my bathrobe at home. All right. The reason why it's able to maintain the osmotic gradient in an energy efficient way is because various solutes, salts and urea, become trapped in the deeper medulla. And the solutes are part of this osmotic gradient. Okay. How does it do it? Remember, this is blood. This is filtrate and interstitial fluid. This is blood. Because this is a capillary. And the thing that blood has that filtrate and interstitial fluid doesn't have is a bunch of these plasma proteins. So this is second bullet on slide 58. Now remember, I mentioned this when I talked about the plasma proteins and albumin, that this is specific osmosis when it comes to plasma protein. This is oncosis. Or the force is what we refer to as oncotic pressure. It's the osmosis when the solute that the water is following is plasma proteins. And because of that, and you can see that's in parentheses there in the second bullet, there's always going to be more solute in the blood, even as it's doing this turn. Because as it's doing this U-turn, just like the nephron loop, there's going to be salt that's equivalent to the interstitial fluid. And it does get salty inside the vasa recta, but there is plasma proteins in the vasa recta that is not in the interstitial fluid. So look at this figure on the bottom of page 58. And I guess I should draw this up. Let me draw it a different color. And since it is a true capillary, I'm going to make it look like that. So this is the descending limb, and this is the ascending limb. So when we have water going, or basically we have a salt, and if you look at this figure on the bottom of 58, you have the nephron loop in yellow, and you have the vasa recta in red. Basically, you're going to have solutes, and yeah, this is same kind of thing as over there. You have solutes coming out here. The difference is it's not staying in the interstitial fluid. It's going back in the descending limb, and these solutes are constantly making a circle. They're traveling down the loop. As soon as it goes back up, it comes out, and it goes right back in. Then it makes a turn and comes out, goes back in, and it makes a turn, goes out, comes back in, and the driving force of this is oncotic pressure because of the plasma proteins. And so when you look at the slide 59, be sure that you understand that's not a nephron loop in slide 59. That is a vasa recta. And water is also actually going in the opposite direction. So the blue arrows here is water. Red arrows are about solute. What you have in the blood vessels are plasma proteins. Always a little saltier in the, especially in the ascending vasa recta. So if you look at the numbers on slide 59, you can see that the numbers on the, especially in the ascending vasa recta, is always saltier because it's getting the salts from around the interstitial fluid, but it also has the plasma proteins in it. Okay. Let's go back over here. Key here is the countercurrent multiplier makes the osmotic gradient, and then the exchanger maintains it and keeps it in an energy efficient way. All right. Now let's go to some pretty established clinical tests that we have done for these, especially these three nephron functions. And this is also part of the course outline where we need to talk about glomerular filtration rate. Glomerular filtration rate is also referred to as plasma clearance. It is the ability of the kidneys to eliminate a given substance from the blood, from plasma, over a specific length of time. Remember, rate is always over time. Okay? Now, there's some things that we need to do to calculate GFR. We need to have the rate of urine formation, and the links for next week's Lab 15 on renal physiology will come out Friday, because that's for next week. And one of the tests for 15B is volume rate, which is basically very similar to this. The first diamond, rate of urine formation. We need to measure the concentration of a certain substance in the plasma, and then we have to measure the concentration of that same substance in the urine. Okay? And if we have this, and these are some typical numbers here for urine formation rate, and then on slide 62, we're going to use a polysaccharide of fructose. This is the given substance for measuring GFR. And the reason why is because this inulin is inert. It's inert to the nephron. It's indiscriminately filtered like everything else that is not too big in the glomerulus, number one, but it is neither reabsorbed nor secreted. It's inert. And so if we can do these measurements, since it's not going to go through steps 2 or 3, it's only telling you about step 1, glomerular filtration rate. Okay? So the amount of inulin excreted per minute is the amount filtered per minute, because it is neither reabsorbed or secreted. So inulin clearance equals GFR. And this stuff is also discussed on page 71 of your lecture packet, page 71. Right? So we inject the inulin, mark the time. We collect urine and measure the urine rate. We'll call that V. This is all on slide 63. And then we're going to measure the inulin concentration in the urine. We'll call that U. And then we'll have to also measure after a specific amount of time the inulin concentration in the blood and plasma, and that's P. Then we just do the math. And these are very classic numbers for adults. 2 milliliters per minute, which is somewhat around average for the example I gave in the Lab 15 PowerPoint, around 2 milliliters per minute. The urinary concentration is around 30, and then there's only 0.5 milligrams per milliliter in the plasma. You do the math and it comes to be about 120 milliliters per minute. Okay, so we will use inulin to check to see how your 2.4 glomeruli are working. 2.4 million of these guys. But there are other chemicals that are selectively reabsorbed, say like glucose, and some substances that are secreted. And we can use the same formula to check the other two nephron functions. Remember, 1 through 3 are nephron functions. But inulin is used for glomerular filtration rate. Step number 1. If we use glucose, using it the same way, we can measure how effectively your nephrons are reabsorbing. And as long as the concentration of glucose is underneath the transport maximum, as you can see here from the figure in your, from the textbook, slide 65, you should have 0. But any number that is less than the number for inulin will be things your nephrons are reabsorbing. And then we have some chemicals like PAH, which are actively secreted. So if you look at slide 66, on the bottom right, you'll see this 625 that is greater than 120. So any number less than 120 are things that are reabsorbed. That's why there's less in the P. If there's any number greater than 120, those are things, chemicals that are secreted. And that's why it's greater. And so from your textbook, slide 67 has a table, 18.3, and it's showing you that. Again, they have inulin at 125. It's all about the same. But anything that's greater is secreted. Any numbers that are less are reabsorbed. So we're going to talk about regulating hormones on Monday, and that's good because that is actually relevant for Lab 15 next week. But other things that can influence the amount of urine and also what's in them. One is blood pressure. The filtration is driven by blood pressure. So if the afferent arterial blood pressure drops too low, this GFR is going to go down. Also, solute concentration. If you have too much salt in your diet, your interstitial fluid is going to be even saltier than the 1400. And that's going to cause water to follow the salt, and the amount of urine production is going to decrease. That is why, if you do this long enough, why you end up with high blood pressure. You should be peeing out this fluid. Instead, because it's too salty, you're reabsorbing it, and it's staying in your pipes. And if you put more fluid in your pipes, the water pressure goes up. Same with blood pressure. Diuretics. Diuretics can either be an intentional pharmaceutical goal or it could be a pharmaceutical side effect. Diuretic is any chemical that causes your urinary volume rate to go up. Okay? You make more pee. I will tell you that there are direct diuretics and indirect diuretics. The direct diuretics are in the figure on the bottom right. Direct diuretics directly work in the nephron. Okay, and those are a lot of the drugs that people take for high blood pressure medicine. It's not all of them, but for some of them. Like thiazide diuretics there in green is a high blood pressure medicine. If you pee more out, you're taking water out of the pipes, and your blood pressure should go down. They, first of all, will want you to control how much salt is in your diet. Once you've done that and your blood pressure is still too high, and they can see that your blood volume is pretty high, they'll give you diuretics to help take some fluid out of your pipes. Okay. Indirect diuretics. So a direct diuretic's a good illustration of that, and it's not listed on this picture on the bottom right, but caffeine, that's why you have that venti Starbucks, why you have to pee in about an hour. Your caffeine and coffee has a direct diuretic effect on your nephrons. The same thing also goes if you have beer. If you have a couple beers, pretty soon you're pissing water. I mean, not only are you pissing a lot, but it's almost clear. It's not even yellow. And that's because alcohol is an indirect diuretic we'll talk about next week. It doesn't affect your nephron, it affects your brain. And since your hypothalamus is part of your brain, it causes there to be a decrease in ADH release from the posterior pituitary. And that's going to cause you to pee a lot. It's not acting directly on the nephron, so it's an indirect diuretic. Okay. Now the fourth bullet is connected to the first bullet. It's just when the blood pressure drops below a certain threshold, you will get kidney failure, and that's shock. And then again, starting on Monday, we'll talk about hormones that regulate that. All right, are there any questions while I show you close-ups of the whiteboard? In the pages from the lecture packet, the fork in the road, the green numbers are the 4 renal functions for serum nephron functions. And then the middle bank, which is the countercurrent multiplier and exchanger. The drawing that is on the whiteboard on the left is the nephron loop of Henle. But this drawing on the right is of the vasa recta, still having an ascending and descending limb, but that is blood. Okay. We got 2 more weeks. This is week 15. Next week we have week 16. Oh, I got to post next week's PowerPoint. And then 1 more week after that, and then finals. No questions? All right. See you next time.